Hello everyone, my name is Santhosh. Today I am going to present the final project of ADTA 5550, a deep learning approach for image classification. Deep learning has transformed computer vision by enabling machines to learn patterns from raw image data. In this project, we focus on convolutional neural network CNNs. For image classification, CNNs are widely used in various applications such as facial recognition, medical diagnosis, and autonomous vehicles. This project specifically explores CNN performance on CFAR-10, a dataset with 60,000 small color images categorized into 10 classes. We also analyze urban sound 8K, an audio dataset converted into spectrograms for CNN compatibility. Unlike traditional high-level libraries like Keras, this project uses TensorFlow 1.xx directly. Implementing the CNN without Keras helps in understanding low-level operations, manual weight updates, and back propagation mechanisms. The objective is to design, train, and optimize a CNN that can effectively classify images from CFAR-10. Additionally, we compare its performance with MNIST, a simpler dataset of handwritten digits, to understand the impact of dataset complexity on deep learning models. The presentation will cover dataset selection, CNN architecture, training process performance evaluation, possible improvements. By the end, we will discuss challenges, optimizations, and feature enhancements to improve CNN accuracy. Introduction to Deep Learning and CNNs. Deep learning is a subset of machine learning that uses neural networks with multiple layers to learn complex patterns from data. CNNs are specialized type of deep learning model designed for image processing, pattern recognition. Unlike traditional machine learning models that require manual features extractions, CNNs automatically detect edges, textures, and objects that convolution operation. This makes them highly effective for computer vision applications. The core strength of CNNs lies in their ability to use convolution layers, pooling layers, or fully connected layers to progressively extract meaningful information from an image. The deeper the network, the more abstract and redefined its understanding of visual patterns becomes. CNNs have been widely adopted in medical imaging, detecting diseases, autonomous driving, object detection, and security systems, facial recognition. Their adaptability makes them crucial for various industries. In this project, we build a CNN using TensorFlow 1.xx without Keras to gain a deep understanding of low-level deep learning operations. This approach in learning how weights are updated, propagation works, and models are optimized. TensorFlow implementation. The primary objective of this project is to design, implement, and optimize a CNN model that classifies image from the CFA 10 dataset We also explore audio classification using urban sound 8K dataset, converting into spectrograms. One of the key challenges is training the CNNs using TensorFlow 1.xx without Keras, ensuring that layers, activations, and optimizations are implemented manually. This approach provides a fundamental understanding of how CNN process data at low level. The project also aims to compare the performance of the CNN on different datasets, including MNIST handwritten digits and CIFAR 10 natural images. This comparison will highlight the difference in dataset complexity and CNN performance. Another important aspect is optimizing the CNN model. To improve accuracy initially, the CNN reaches 69.67 accuracy on CIFAR 10, but by adding an extra convolution layer 128 filters, with 128 filters, the accuracy improves to 70.88%. The final scope of the project includes exploring future enhancements, such as using deeper architectures, REST VGG, advanced optimizers, atom dropout layers, and data augmentation techniques to improve model performance. Data preprocessing. CIFAR 10 dataset. CIFAR 10 is a widely used benchmark dataset for image classification. It contains 60,000 color images in 10 different classes. Each image is 32 into 32 pixels, making it a challenging dataset for CNNs due to its small size and lack of detailed features. The dataset is divided into 50,000 training images and 10,000 testing images. The 10 categories include aeroplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. The goal is to classify each image into one of these classes. One of the main challenges with CIFAR 10 is intra-class variability. For example, different dog breeds look very different, making it harder for the model to learn distinguishing features. Additionally, background noise, lighting variations, and small image size make classification difficult. The Urban Sound 8K dataset is used as secondary dataset, where audio files are converted into spectrogram images for CNN processing. This allows CNNs, which are traditionally used for images, to classify audio signals visually. Preprocessing is essential for both datasets. CIFAR 10 images are normalized to have pixel values between 0, 1 for better training stability, while Urban Sound 8K audio files are converted to frequency domain spectrograms before classification. Data preprocessing is a crucial step in deep learning as it enhances model performance and reduces computational complexity. For CIFAR 10 preprocessing includes normalization, splitting into training and testing sets, and batch-based data loading. These steps ensure that model learns efficiently without being affected by large variations in pixel intensity. Normalization is applied to scale pixel values to range of 0, 1 since raw image data contains pixel values between 0 and 25 to 255. Normalizing them ensures the that the model learns more efficiently, learning to fast convergence. Without normalization, weight updates in CNNs can become unstable. The CIFAR-10 dataset is divided into 50,000 training images and 10,000 testing images. This allows the model to learn from a large amount of data while having enough test samples to evaluate generalization performance. Splitting dataset properly is essential to avoid overfitting. For urban sound AI game, the raw audio files are converted into spectrograms. To make them compatible with CNNs, a spectrogram represents the frequencies content of signal over time, allowing CNN to learn sound pattern visually. This approach is widely used in speech recognition and environmental sound classification. Future improvements in pre-processing could include data augmentation techniques such as random cropping, rotation, horizontal flipping, and contrast adjusting. These techniques artificially expand the dataset, helping the CNN generalize better to unseen data. CNN architecture. The convolutional neural network CNN used in this project consists of multiple layers, each designed to extract relevant features from images. The architecture follows a traditional CNN pipeline with convolution layers, pooling layers, fully connected layers, and a softmax output layer. The first convolution layer applies 32 filters with a 3 by 3 kernel size. This layer detects basic patterns like edges and textures in the image. The ReLU activation function is used to introduce nonlinearity, helping the network learn complex patterns. The second convolution layer applies 64 filters with a 3 by 3 kernel size. The deeper the layer, the more complex the feature it learns. This layer focuses on extracting more refined details such as shapes, object paths, and textures. Pooling layer, max pooling with a 2 by 2 window are added up after each convolution layer. These layers reduce the spatial dimension of the features, maps making the model computationally efficient while retaining the most important information. The final stage includes fully connected dense layers with 128 neurons, followed by an output layer with 10 neurons. One each class is C for 10. The softmax activation function converts raw scores into probabilities, allowing the model to learn to classify images correctly. Training the model. Unlike Keras, TensorFlow 1.xx requires manual implementation of CNN layers, activations, and optimizers. The model was built using low-level TensorFlow functions, ensuring a deeper understanding of how CNN competitions are performed. The convolution layers were implemented by using tf.layers.convolution 2D, where filters, kernel size, activation functions, and padding options were manually defined. This approach ensures fine control over feature extraction. The training process involves defining the loss function cross entropy loss, which calculates the difference between the predicted output and actual label. The loss value is minimized using gradient descent optimization. The model is trained in batches of 128 images, meaning that instead of processing all images at once, the model updates its weights gradually after processing each batch. This technique improves convergence and prevents memory issues. Manual weight initialization and optimal tuning were crucial in achieving better accuracy. Adjusting learning rates, batch size, and adding regularization techniques like dropout could further enhance model performance. The CNN performance metric. The CNN model was trained for 5,000 iterations with accuracy evaluations every 100 steps. Initially, the model's accuracy was 10.27, which is equivalent to random guessing. Since CIFAR 10 has 10 classes, after 100 training steps, accuracy improved to 42.54, indicating that the model had started learning useful patterns. The network gradually refined its feature maps, leading to better classification. By step 2000, the accuracy reached 68.41, showing a consistent improvement in the model's learning ability. However, accuracy gains slowed down as the network approached its performance limit. The final accuracy after 4900 steps was 69.67, meaning that the model successfully learned to distinguish most image classes, but still had room for improvement. Adding more filters, deeper layers, and advanced filters optimizers could help boost accuracy. One challenge observed was misclassification in visually similar classes, such as cats versus dogs or automobile versus trucks. This suggests that model could not benefit from data augmentation and larger architectures like RESTnet or VGG. Comparison with MNIST dataset. The CNN model was also tested on MNIST. It is a dataset of handwritten digits 0 to 9. Since MNIST consists of grayscale images with simple shapes, the model performed exceptionally well, achieving 98.9% accuracy. Compared to CIFAR 10, 69.67 accuracy, MNIST was significantly easier to classify. This is because digits have clearer boundaries and less background noise, whereas CIFAR 10 images contains complex objects with varying textures, lightning, and occlusions. A key takeaway is that CNNs perform better on structured, simple datasets, but struggle with small, diverse, and cluttered images. CIFAR 10 requires deeper models and more training to achieve high accuracy. The results highlight the importance of dataset complexity in deep learning performance. While a basic CNN can achieve high accuracy on MNIST, a more advanced architecture is needed for CIFAR 10. Future improvements could involve testing on complex datasets like ImageNet or using transfer learning from pre-trained CNN models to improve accuracy on CIFAR 10. Challenges with CIFAR 10. To improve accuracy, an additional convolution layer large intra-class variability. Example, different dog breeds look differently, and small size pixels limits are like fine-grained features extraction. Different lightning conditions viewpoints increase classifications difficulty. These are the challenges with the CIFAR 10 dataset. Enhancements. To improve accuracy, an additional convolution layer 128 filters was added. This helped the network extract more complex features, leading to an improved final accuracy of 70.88%. This enhancement allowed the model to recognize fine-grained patterns, while improved classification in difficult cases like cats versus dogs. However, increasing network depth comes at cost of higher computational time. Training took longer, but the accuracy boost justified the added complexity. A future enhancement could involve adding dropout layers to reduce overfitting. This would ensure the model generalize better to unseen dataset. Another approach is to switch from stochastic gradient to Adam optimizer, which could further improve convergence speed and accuracy. Future enhancements. Data augmentation. Applying rotation, cropping, and flipping to expand training data artificially. Advanced optimizers switching from stochastic gradient descent to Adam optimizer for better convergence and stability. Dropout layers, preventing overfitting by random disabling neurons during training. Transfer learning using pre-trained models like ResNet, VGG for improved feature extraction. Hyperparameter tuning, adjusting learning rates, batch size, and layer configurations. Key challenges. CIFAR 10 images have low resolution, 32 by 32 pixels. Large intra-class variations makes classification more difficult. Training deeper networks increase computational cost. Enhancements implemented. Added an extra convolution layer for better feature extraction. New accuracy 70.88% compared to 69.67%. Future work, implement ResNet and VGG architectures to improve performance. Applying transfer learning with pre-trained models. Introduce dropout layers to prevent overfitting. CNNs are effective for feature extraction, but deeper architectures for complex datasets. Dataset complexity affects accuracy, MNIST versus CIFAR-10. Future improvement, data augmentation, ResNet, VGG dropout layers. TensorFlow 1.xx provides greater flexibility but requires optimization. The completion of this project has coming to the conclusion. The completion of this project has provided valuable insights into deep learning, CNN architectures, and dataset complexities. By implementing a convolutional neural network from scratch using TensorFlow 1.xx, we gained a deeper understanding of low-level deep learning operations, manual weights, updates, and optimization techniques. Unlike high-level frameworks like Keras, this project required explicitly defined layers, activations, and backpropagations, reinforcing the core concepts of deep learning. One of the key findings from this project was the impact of dataset complexity on CNN performance. The CNN achieved 98.9% on MNIST, a dataset consisting of grayscale 100 images with well-defined shapes and minimal background noise. However, when applied to CIFAR-10, a dataset with small complex color images, the accuracy plummeted at 69.67%. This demonstrated that while CNNs perform exceptionally well on structured datasets, they require deeper architecture and additional optimization techniques for more complex datasets. To enhance model performance, an additional convolution layer, 128 filters was added, improving accuracy from 69.67% to 70.88%. This modification allowed the network to capture more detailed spatial patterns, leading to better feature extraction. However, the trade-off was an increase in computational complexity and training time. This reinforces the idea that CNN depth must be carefully balanced against performance efficiency to achieve optimal results. One of the main challenges encountered was misclassification in visually similar classes. For instance, the model struggled to differentiate between the cats and dogs or automobiles and trucks primarily due to small size, 32 by 32 pixels, and variations in object performance, light and background clutter. This highlights the need for advanced CNN architectures, transverse learning, and data augmentation techniques to improve classification performance. CNN effectively extract features from both images and audio. Data complexity significantly affects model performance. Advanced architectures like ResNet can further improve accuracy. Here, this project's valuable insights into functionality and optimization strategies. Thank you for your time. I'm happy to take any questions.